action as a function of q's and q's. Okay? Then you try to evaluate the equations of motion obtained by varying that action. Use Lagrangian's equations for now for the variables qn and qn. Okay? That will give you a second set of equations. These two sets of equations have to be equivalent. Because both of them express the same physical condition, namely the condition of extremization of the action. Is this clear? No, good question. So that's a good question, but that's not right. You see, the Lagrangian, the action is an integral. And I can redefine the action in any coordinate system. Now, Arjun's question was, suppose you redefine the Lagrangian in terms of some funny coordinates, then what happens to the translational invariance of the motion? Such that? No. See, so I'm going to do an arbitrary change of coordinates. For instance, if I move to spherical polar coordinates for each of the particles, translational invariance is not manifest. The spherical polar coordinates is an actual origin. Okay? But I can do that. Nobody can stop me. Okay? Now, the invariance of translations is still there though. Because if you took the action and moved all x's, that corresponds to some operation on your q's. It could be a pretty weird operation on your q's. But since the potential was invariant under translations and x's, it is also invariant under the corresponding translation in q's. Okay? So the invariances of a problem are not lost, but they may not be manifest. So there are two separate things. If you make the kind of transformation that you're talking about, namely just a translation by x's, then you will move to a new set of coordinates in which the action will have the same form as the action in the old set of coordinates. That is the situation when you have symmetry. That's a very simple kind of coordinate transformation. But nobody can stop you from doing other coordinate transformations. Changes of variables exist. The action does not have the same form in the new variables as the old variables. Symmetries that were manifest in the old set of variables may not be manifest in the new set of variables. But it's the same physics. You're representing the same integral in terms of some different quantities. And the condition for extremization is physically the same. Is this clear? It's very important. Okay? The action formalism of classical mechanics is not in any way tied to a particular set of quantities. Okay? It's an integral which the basic principle is extremize an integral. Okay? And you can choose to work in any, you can redefine the functions in that integral any way you want. That basic principle does not change. That integral is a number, it does not care about coordinate changes. Is this clear? Manifest, we'll talk about that in manifest is, you look at the Lagrangian and you can see that it's you may have to work hard to realize it. It's just an imprecise.
I just have one question. So
yes.
Is there any a priori reason that we separate the velocity dependent part of this?
There's no terribly good reason. There could be interactions that depend on velocities. And when you study electromagnetism, it's interaction with the magnetic field. And that does happen. We're taking a simple example for now, which we will later generalize. This is not meant to be the most general thing. Okay? We've got a Lagrangian on the board just to be self-confident. Fine. But we'll stick to this for a while before taking this. Okay. Now, the next thing I wanted to do was, so my plan was to have two sort of abstract-ish lectures. This is the same with these abstract-ish lectures. And then we're following this really lovely book, it's Lagrangian. One of the lovely things about it is there is a set of lovely problems, all of which have answers. Okay, so we work out in the board, maybe in class 3, a few of these problems, just so that you get the hang of doing things. Maybe that will make it less abstract. Okay, so if you're not used to thinking so abstractly, and I mean abstractly as opposed to mathematically, it may be a little unsettling, some of this, but you'll get used to it, and it's a good way. Okay, and we'll make it more complicated soon. Maybe not next lecture. Let's get frustrated. Okay, now, the next thing I want to talk about is about symmetries in quantity. Okay. This Lagrangian here has a bunch of symmetries, and there is a very beautiful fact about classical mechanics that actually extends to quantum theory, which is the statement that whenever an action or a Lagrangian has continuous symmetries, there is a conserved charge corresponding to that continuous symmetry. Okay? This is called Noether's theorem. Okay? I'm saying it colloquially first, I will explain it precisely in a minute. But the colloquial statement is that corresponding to every continuous symmetry in a Lagrangian, there exists a conserved charge. So let's make both these statements more precise. Okay? What is a continuous symmetry? First of all, what is a symmetry? This is related to Arjun's question. A symmetry is a change of coordinates such that the form of the action in the new coordinates is the same as the form of the action in the old coordinates. Okay? So, a symmetry is a change of variables. X prime. Okay, I'll be abstract now. Let's deal with some check. There are a bunch of coordinates qk. These qk's could be these x and i's, could be anything else. You've got a Lagrangian written in terms of some coordinates qk and that derivative. So suppose you make a change of coordinates such that q is some function of qk. So if the Lagrangian if the action was of the form dt L of qk dot, let's say qk prime dot, this coordinate, and then you plug this coordinate, this definition here into this integral and work it out to express it as a function not of q prime but of qk. It turns out to be the same dt L of qk. Suppose this happens. If this is true, this is in general not true. If this is true, then the coordinate change this one is called a symmetry. Okay? So just to fix the ideas in your head, suppose we took a simple Lagrangian, let's say we have x dot squared by 2. One part, free part, mx dot squared by 2. Now, I'm going to make two different coordinate changes. The first one is x is equal to x plus a. And the second one is x is equal to y squared. X of t is y of t the whole squared. X of t is y of t plus x of a. But you understand, when everything is functional, the same thing. Okay. Now, can you tell me which one of these operations is symmetry, the other one is not? Which is a symmetry? X plus a. Exactly. Let's just check. So x. Sorry. Okay. X dot is equal to y dot. because A is a constant, it's not a derivative. And so if I just take this coordinate change and I plug it into the action, I once again get, implies S is equal to M by 2 y dot square. But this is the same function of y dot as the original action, or this function of x. Therefore, it's a symmetry. By definition. On the other hand, this coordinate change will make the action, well, let's say x dot is equal to 2y dot, which implies that S is equal to 2m y dot square, the whole thing square. Remember? This is not the same functional form of y and y dot as this action was of x and x. Is this clear? Okay, therefore this coordinate change is not a symmetry, whereas this coordinate change is. Okay? So you understand what I mean by symmetries? Yes?
Even if the functional form may not be the same,
Yes.
the integrals might not be the same.
No, we're saying up to things that are zero under integration. You see, I'm not, so maybe I should say, if it can be massaged into the same function. You know, you can always add something that's zero. But that's, you see that it's zero. So I was careful to say that the action should be the same, not the Lagrangian. Should be the same. Okay. Now, suppose, what is the importance of symmetries? The first importance of symmetries is this, that if you have a symmetry, then that allows you, and you have one solution to the equation solution. Then, I should say before, so far I've talked about symmetries, but in my description of this theorem, I use the term continuous symmetries. What do I mean by that? A continuous symmetry is a one parameter set of symmetries, one parameter set of coordinate transformations, that includes the identity transformation. That is, x is equal to x of y, comma some parameter, let's call it lambda, such that when a lambda equals 0, this coordinate change is trivial. X is equal to y is equal to x. But as lambda changes, it becomes non-trivial. Okay? So the coordinate change that has a point which is doing nothing, no change, and can be infinitesimally moved away from doing nothing. Okay? So the coordinate change that we talked about here, this was continuous symmetry because there's a parameter a. When I take a to 0, this just becomes x is equal to 1. This kind of transformation has no obvious parameter in it. Okay? And of course it was not a symmetry, so we wouldn't quibble about whether it's a continuous symmetry or discrete symmetry, because it's neither. But the first one is a continuous symmetry. It's a parameter which when taken to 0 gives you the identity. Okay? Fine. So now, what is the importance of symmetries? Well, firstly, there's this obvious but nonetheless interesting and important statement, which is that, look, suppose you have one solution of the equations of motion in your variables q. So qi is equal to some specified function of time, solves the equations of motion. But since the Lagrangian is the same form in the variables q prime as it had in q, therefore the equations of motion for q prime are the same as those for q. Since the action is the same form, the equations of motion for q prime are the same as those for q. Therefore, q prime being equal to the same functions is also a solution to the equations of motion. Okay? So let me say that in equations. So, if qi of t was equal to fi of t, solves equations. Then qi prime of t is equal to fi of t, also solves equations. the same physical solution. If you try to evaluate what Qi of t was on this solution, it would not be Fi of t. Right? Because Qi of t is some function of Qi prime of t. Oh, let's get vice versa. Is this clear? Okay? So, the fact that Qi prime of t equal to Fi of t is a solution. Now, if you take this and use it to solve for, implies that Qi of t is equal to some F tilde I of t. Is also a solution, where F tilde is obtained by plugging this solution into okay, sorry. Let me say it as clearly as I can. So, this one was Qi prime, and this guy was Qi. Now, take this solution and plug it into the relationship. Okay? So, what you get is Qi prime is equal to which Ram's function? Excellent. Is equal to Qk, Qi, my notation is there, right? Qi of Fi of t is also a solution. Okay, I said this unnecessarily confusingly because my notation is unnecessary. Okay. Qi prime was some function of the Qi's. I called that Qi prime itself, but I could rewrite this as Gk of t. Okay, then it'll be clear out. This is Gi of Fi of t is also a solution. Right? Because if Qi is Fi of t, then by definition Qi prime is Gi of Fi of t. But Gi of Fi of t is not the same thing as Fi of t. So we've got two different solutions now in the Qi prime points. So what I'm saying is actually very obvious, but just to say it again, a symmetry allows me to take old solutions to the equations of motion and generate new solutions. Okay? Of course, it could sometimes happen just by chance that when you apply the symmetry transformation to a particular solution, it does not change, it gives you back the same solution. That's possible. But most often that will not be true. So let's take an example. Suppose you've got a bunch of particles and they're moving around. So what does symmetry under translations allow you to do? It allows you to get new solutions by taking this whole bunch of particles, moving them here, and let them move around in the same relative way. But just overall moved to a different place. Okay? Suppose something's moving around in space. Symmetry under rotations allows you to move this thing to move around like this in space instead. So they rotate in this direction. Okay, so what we've said is very intuitive. And of course, it's the reason we call this thing a symmetry. You know, our idea of symmetry is if you do an experiment here, or if you do the experiment here, you get the same answer. And that's what we say in complicated mathematical language. Or if you do the experiment pointing your parameters there, or you use the experiment pointing your parameters there, you get the same answer. That's what we say. Alright? Fine. So this is the obvious thing about a symmetry. And it's the reason we were interested in symmetries. But there's something less obvious about symmetries. And that is that every continuous symmetry is associated with a conserved symmetry. This is the thing we now want to understand. Okay. There were less questions today than last time. I hope this doesn't mean that I'm losing. What? Okay, go through this. Yes. Good. Suppose you know that Qi prime of t is equal to Fi of t, some function, solves the equation of motion. Then it must be true that Qi is equal to the same function of t also solves the equation of motion. Because the Lagrangian the action is the same form in Qi and Qi prime, and therefore the equations of motion take the same functional form in Qi and Qi prime. Okay, so it's prime coordinates. So it's qi prime is equal to gi as a function of fi. This is a new solution now. You get some new functions here as compared to fi. So you generate not just one solution, any one solution can then be mapped to another solution by this procedure. If you have a continuous symmetry, you map it to one parameter set of solutions. Physically, for translations, this was just the solution you get by translating the solution in space. Or by rotation, by rotating the solution in space. Is this clear? Yes?
Can you do this like iteratively? For example, we have a solution q prime of t is equal to ft t, and then we have a corresponding solution for qt, the original coordinate. Now, can we do this iteratively?
Make precise, I don't understand. Yeah,
I think what?
Good. Give two different symmetries. Then this question of doing this one first and then the other one. Or the first one and then the second one. And then there's an interesting question of whether we get the same answer. And maybe that's what you're leading towards. There is an interesting answer to that question, as some of you know. Structural groups, in some sense. But okay. Good. Other questions, comments? No, they have a unique solution given particular initial conditions. Given q and q dot at a given time, then they have a unique solution.
We started with the action at t equal to t0, q equal to t0, and t equal to t, and then we have two solutions.
Right. So these coordinate transformation need not preserve the boundary values of your action. In general, it will not. Suppose we do translations. Okay? Then, if x originally was 0 at time t equals 0, then under that coordinate change, x will be a at time t equals 0. So it's not preserving the boundary conditions of the action, but it's preserving the form of the action as an integral. Now, although we use the boundary conditions and the action in order to specify the principle of least actions, you remember that the equations portion you got in the end made no reference to the boundary. Okay? So all that we require for something to be a symmetry is that it preserve the form of the action. Okay? In general, this coordinate transformation does not preserve the initial conditions. Okay? And therefore, you move from one solution to another. And the way that's consistent is that we move from one initial condition to another. Excellent. Good question. Other questions, folks? Okay. So, let's move on. Now we want to understand that the less obvious thing happens with symmetries. And symmetries are also associated with conserved charges. Now, the argument I'm giving is going to be a little abstract, but it's very beautiful. And let's see how it goes. So, suppose you have qi is equal to these primes will give. Okay, let's call qi prime is equal to qi plus, suppose you've got a continuous symmetry labeled by some parameter epsilon. Okay? And choose epsilon to be very small and work to first order epsilon. So look at those symmetric transformations that are near to the identity. Okay? Plus epsilon aij of qj. This is a function of qj. Now, that is ai of qj. Okay? So whatever the symmetry is, I take an expanded and Taylor series in the parameter about epsilon equals 0. Epsilon equals 0 is the place where you have the identity. Okay. So we have qi prime is equal to qi plus epsilon times ai of q's, of the q's. This here is understood, this function of all q's. Okay. This we are given is a symmetry of R. Suppose we know that this is true. Okay? Given is a symmetry. What does this mean? It means in particular that since we work only in first order in the coordinate change, we should work only in first order in the form of the action. Because the form of the action does not change at first order in absolute. Okay. So it means that S of qi prime dot is equal to S of qi dot plus order epsilon squared. In functional form. Okay? Now, let's translate this condition to an equation called Lagrangians. Two actions can be equal if the Lagrangians differ by a total limit. Okay? So, we want this statement here is that S of L. So the Lagrangian as a function of qi prime and qi prime dot is equal to Lagrangian as a function of qi dot plus epsilon times d by dt. That's some function, let's call it h of qi's plus all the epsilon. Okay? Excellent. Now, this is true. This is what we mean by saying unquotable transformation. Was a symmetry. For instance, in the case of translations above, the function h was 0. The Lagrangian itself was just invariant. Okay. Now, we do something a little fun. We do the following. We consider the coordinate change. Qi prime is equal to qi plus epsilon of t. Out. Where epsilon of t is a small function. And we'll work this first order in epsilon. We got products of this function itself. Now, this is not a symmetry. It's not true that this keeps the form of the action. Then, if you translate in space by a time-dependent translation, you change the form of your action. Okay? But we know that it is a symmetry when epsilon reduces to a constant. So what does that mean? That tells us that under this coordinate transformation, which I'm of course free to do, I'm free to do any coordinate transformation. Okay? L of qi and qi prime and qi prime dot is equal to, well, what we have then, L of qi dot plus epsilon of d by dt I plus something like this. That something else is only first order in epsilon, because we're throwing away second order terms, and has to vanish when epsilon becomes a constant. Okay? And so can be written as epsilon dot times ai, no, times let's call it g of Now, you could also have terms that are epsilon double dot and so on in general, but I'm interested in this under the integral side. So if there were higher order terms of time derivatives, I'll integrate by parts and bring all the derivatives that were here and put them in. Okay? So I'm doing this manipulation only for epsilon functions that vanish at the two ends of my action integral, and so I'm allowed to integrate by parts arbitrarily. This I'm free to do because epsilon was a function of time, and I specify that it's a function of time that is 0 at the beginning and the end, at t0 and tf. But it's completely arbitrary. Is this clear?
Why don't we integrate by parts once more and put everything with epsilon?
And put everything with epsilon? That's what we're going to do, right? Okay? Now, as you suggested, let's integrate by parts once more. Okay, good. Now, what is the change in the action then? The change in the action can be thought of as, so delta S is equal to epsilon times d by dt of this h of qi, and then by integrating by parts once more, we get epsilon, the epsilons are there, times d by dt of g of qi and qi. Okay? Which is equal to integral epsilon times d by dt epsilon times d by dt of h minus g. Drop it to the brackets. Okay. So, under such a coordinate change, okay, the change in the action is given by this object. But this is true just as an algebraic manipulation on actions. Now, remember that the on-shell solutions to the equations of motion are such that to first order any change in the function away from a solution does not change the action. Okay? Say. Remember that a solution to the equation of motion was, by our basic postulate, an extremum of the action. What does this mean? If you have a solution to the equation of motion and you change the functions a little bit, then the action does not change at first order in this deformation of your path. Okay? But plugging this thing in here is a first order shift in some object, and so if this object is evaluated on a solution to the equations of motion, it must vanish. Okay? This object in general is not something zero. Okay? As an algebraic manipulation on the action is not something zero. But must be zero when evaluated not for an arbitrary q and q dot, but for a q and q dot that satisfies the equation of motion. Is this clear? That tells us that solutions to the equations of motion have something very special about them. So we conclude that for solutions to the equations of motion, d by dt of, let's call it q, which is equal to 0, where q is equal to h minus g. So there is a quantity that we can construct a priori, and this is very important, without referring to which solution to the equation of motion. Okay? Just by this algebraic manipulation of the action, in time for every solution to the equation. So whenever your Lagrangian, your action has a symmetry, it is true that there is a corresponding conserved charge. Maybe there's some function of q and q dots that is a constant independent of time. Okay. Now, some of you people are thinking, now it sounds like we're being mathematicians rather than physicists. It exists, so it says that there is a conserved charge. That's not very useful unless I can construct it. Practically. But of course, we can construct it. So now the next part of our program is to actually find explicit expressions for these conserved charges. Okay? So let's go. Is this clear, by the way? Questions or comments? Okay. So now let's go. So let's look. This procedure was totally gentle. It was completely gentle. Made no assumption about what form our coordinate change, or what form the coordinate change took. But let's take special cases. Oh. Suppose the asymmetry is such that L itself is invariant. Okay? Then what are we supposed to do in order to evaluate the conserved charge? Then this H function which is 0. So that is it. Then a conserved charge is just a quantity G. So what we are supposed to do is to make the change of variables that corresponds to the symmetry, except we allow the parameter of that change of variables to be time dependent, and isolate out the coefficient of epsilon naught in the changed form of the action. Okay? So let's do that. Suppose our Lagrangian was, okay, let's do it in the concrete context that we've been talking about. That is, remember we've been talking about mi dot squared. But actually, we can do it totally different. So let's just do it. Okay, so fine. So now, look, I'll do the Lagrangian on the board just so that we can see it. Suppose we have mi xi dot squared 2 minus. Okay, so suppose, just as an example, though it's not needed for the logic, a qi for xi. And we do some transformation that is a symmetry if epsilon is constant, but is not if epsilon is constant. Okay? So the action changes a little bit because epsilon was a function of time. Okay? Where do you see that happening? See, suppose you plug in the change of coordinates where epsilon is a function of time, in the potential it doesn't matter. Okay? Because the potential is just an invariant function of the x's as numbers. Any change of the x's of the right form will leave the potential invariant, whether or not it's a function of time or anything else. Is this clear? For instance, suppose the potential was x1 minus x2 mod squared. Then this quantity is invariant under x1 goes to x1 plus a1 and and x2, these are vectors, goes to x2 plus a2. And this is invariant whether a is a constant or time dependent. It's just invariant. And the key point is that the potential has no time dependence. So you cannot distinguish a constant that's independent of time from a constant that's dependent on time by time. On the other hand, this quantity is different. If you make the change, x goes to x plus epsilon of t times a, then this quantity changes in a different way. From x going to x plus, yes, because of the epsilon dot. Okay? So now, keeping this in mind, you see, we want to calculate what the change of this action is that knows about the epsilon dot. Okay? So, the part that comes from the changes in q's is insensitive to epsilon being a function of time. But the part that comes from the change in the Lagrangian q dot is sensitive to it. Okay? So, you have a term that is the change in the Lagrangian, delta L, includes a term that is equal to dl by dqi dot dl by dqi dot times epsilon dot times whatever we call the function j. No, the transformation is there. It's at AI. This is the additional change in the Lagrangian that you get from the fact that epsilon is a function of time rather than being a constant. Is this clear? Okay? Because q dot, qi dot changes, the change in qi dot is equal to what it would have been, epsilon times delta qi dot plus epsilon dot times delta qi. So the full change under this coordinate transformation, so let me say it. Okay, the full change under the coordinate transformation includes the part that you would have got when epsilon was a constant, but new part. The new part is the derivative of the Lagrangian with respect to qi dot times this quantity. Is this clear? Okay? Okay. So, in this case, what do we get? We find that the change in the action is epsilon dot times del L by del qi dot times AI. And this is the quantity, the coefficient of this epsilon dot that we were supposed to identify with this. So it was some good one, right? Okay, so our conserved charge Q is given by sum over I del L by del qi dot times AI. This object is since this was probably confusing, let me say it more clearly. What were we supposed to do? In order to evaluate our expression of the conserved charge, what we were supposed to do is to evaluate the change in the action. Just when it was an algebraic quantity, no variation principle or anything, but just take the action. Evaluate the change in it when I make a particular coordinate transformation. Okay? So let me do it once again, then just with knowledge. The coordinate transformation I'm making is qi prime is equal to qi plus epsilon ai cube. And this is the function of that. So, I'm only going to linear order epsilon. So qi prime dot is equal to what? It's qi dot plus epsilon of t ai q plus epsilon dot ai dot what? This is wait, epsilon dot of star plus epsilon dot of t ai. AI, same thing is? It's a function, it's a derivative of this function, and then you evaluate it by changing. Okay? Fine. Now, I'm supposed to put this in and see how the action changes to first order events. What is the change? We use the chain rule. How does the Lagrangian change? So what we're looking at, because we've assumed that the Lagrangian itself is brilliant. Okay, how does the Lagrangian change? So taking the Lagrangian, del chi to first order is equal to del L by del qi, delta qi, that's this object, epsilon ai, plus del L by del qi dot, epsilon ai dot, plus epsilon dot ai. This is the change in the Lagrangian. But we've been given that this change is symmetric. That is, it's zero when epsilon dot is 0. This tells us that these two pieces by themselves vanish. All that survives is this. Okay? So the change in the Lagrangian under this quadrant transformation is del L by del qi dot epsilon dot times ai. And now we use the fact that the coefficient of the epsilon dot must be a conserved charge, as we are on shell. This is not zero as a function, it's something. But on the equations of motion, this quantity must vanish. Integrate by parts, it's d by dt of that other quantity. This quantity here. Okay? This is no such theorem. Typically derived in a much if you look at Goldstein's derivation, I remember I took a year or so to understand. But that's probably just me. Okay. Okay. Fine. Actually, one really nice thing about this is that this way of thinking of the problem very quickly generalizes to quantum mechanics. When you study path integral and quantum mechanics, it's a very simple path integral generalization of this, which is the way quantum field theorists thinks about it. Okay. Fine. Now, this is nice, but in general we also have changes in the Lagrangian. If you also have a change in the Lagrangian, what is the expression for the conserved charge? Well, we just have to add to this object or subtract from this object whatever you want to change in the Lagrangian. Right? So the conserved charge to be thought of in general is del L by del qi dot ai q minus h. Well, h is the term where h, you remember, was the coefficient, where the change in the Lagrangian for a constant epsilon was epsilon times d by dt of h. This is a general expression. This is the expression for the conserved charge. Now this is very abstract. Let's take it immediately and apply it to our particular. Oh, that's convenient. We have a board here. Okay, so now we'll apply it. To this system. So we knew that this system, we know that this system has many symmetries. Let's apply it first to translations. Relations in space. Okay? What do we get? Well, what is the thing we have to identify in each case is what is AI. Okay. So now what we want is the shift. We want delta A NI. What is it? So somebody tell me? Well, okay, yeah. So there's if we want a translation in space by an infinitesimal amount AI, the shift function that will multiply the infinitesimal is what? It's just some constant AI. Okay, some constant AI where AI can be anything. If you want translations in the one direction, AI is non-zero only in the one direction, zero in the 2 and 3 directions. Okay, it could be anything. Okay, so let's apply this to apply that formula then. So we've got a charge Q that is conserved, which is equal to del L by del X in I dot times AI. This is conserved charge. The del L by del X in I dot is simply equal to mn x in I dot summed over all A multiplied by A. Now this is conserved for every AI. So it tells us that each of the three quantities sum over n mn xi n dot are conserved. These are not functions of time on any such unitary equation. This, of course, is the famous conservation of linear momentum. Right? As you all know from all elementary discussions of these topics, this quantity is the momentum associated with the ith particle. Momentum is additive. It sums over particles. The sum of all momenta is conserved. You already knew this, and you could prove this quite generally by using the equations of motion. Okay? But the emphasis of this derivation of it was to emphasize to you that this is a direct consequence of translation invariance. Every system that has a translation invariance, whether it has this form of Lagrangian or not, will have a conserved charge, which we will call momentum. And that's not interesting, as we've done physics more and more sophisticatedly, the objects of physics change. We've gone from particles to fields and then to quantum fields and so on. But symmetries don't change. And the fact that symmetries need to conserve charges also doesn't change, at least so far. Okay? So, while specific expressions for, say, momentum might vary, the fact that there is a conserved momentum is always true as long as you have a Lagrangian that has translation invariance. So, in a structural way, this is a good way to think of translation. Think of it as a consequence of symmetries. Okay, so that's momentum. Now, we also have rotations. Okay, so what are the what are the rules for infinitesimal transformations under rotations? Well, delta x n I is equal to epsilon I j k, let's say delta x n j times ak. This is an infinitesimal rotation around the axis labeled by ak. This everyone familiar with? Infinitesimal form of SO3 rotation. We'll discuss this in more detail as we go on. Just this stage. Okay, so we put the same expression into. By the way, this quantity, as we've seen, is what we normally call the momentum quantity. This is used with the following terminology. In a general Lagrangian, del by del qi dot is called the canonical momentum with respect to the coordinate qi. In the simple case that we're talking about, it reduces to our usual notion of momentum. In general, the sum of canonical momenta are not constant. That would only be true if you had translation invariance with the qi relations. Okay? But we still use the meaning. Qi dot del the derivative of the Lagrangian with respect to q bar dot is called the canonical momentum with respect to q bar. Okay, so a way of saying this part of the expression for the conserved charge in words is that the conserved charge is the canonical momentum with respect to each coordinate times the infinitesimal shift under the symmetry of that coordinate, summed over all coordinates. And then you add to that or subtract from it the change in the Lagrangians. Okay. Now, excellent. So we've seen that where were we? Rotations. Okay, I'm getting worried about the lack of questions. Does this mean I'm going too fast? Is there something I can do? Has it got to a point that you're not understanding things so badly that you can't tell? You don't know what you're I may be going too fast. I'm not terribly sure what the background level is. I'm giving these lectures more or less assuming that all of you have seen an elementary version of these things before, roughly. And I'm trying to say it in a way that I think is nice. So it would be too fast if you've never seen it. Are you getting lost, please? It's fine. Okay, so now we look at the rotations. So as Q is equal to del L by del X n I times epsilon I j k delta x j times now okay. Okay, sum over I. So this is just the momentum, not delta x. This is x. Sorry. The change, there's an epsilon, yes. Small change is proportional to the actual position, not the change. Sorry. So this Q here once again we do the sum over n. This is epsilon on the right hand side of Q. Epsilon on the right hand side of Q. Epsilon side of Q. This epsilon. Yeah, but you see, if a number times something is conserved, then that thing is conserved. See, and we take away that small number. Okay, so what is this? This quantity up to a sign. Signs are not important because of quantity is conserved minus that same quantity is conserved. This quantity is sum over I R cross B. The vector components are sum over I. Because this guy isolates which component you're looking at. And this is R, this is P, and they're joined together by an epsilon. Epsilon is the thing that gives you the cross product. Well, they need to be serious. Let me show you if I said epsilon. Sorry, I should have said this. Epsilon is the completely antisymmetric object. Let me show you. Yes. It's long. Yeah. Okay, good. So, sum over I, R, I cross Pi. And that is, of course, the angular momentum. The usual notion of angular momentum. Again, it's not at all difficult matter to just take d by dt of this quantity and check using the equations of motion that is considered. Okay? So, again, the achievement of this way of thinking of it is not so much that you didn't know that angular momentum was considered, or you did. It's to see how it comes from symmetries. Okay. Now, I'm also okay. Now, there is another symmetry in our problem that we have not yet explored. See, invariance under time transformations. What is the conserved charge corresponding to that? Anybody? Energy. Let's see how that works. Okay, so what is delta? So these two discussions depended on having this form of the action, because we wanted translational invariance in the x, and that was true only in the x coordinates. We wanted rotational symmetry, and that was true only in the x coordinates. But time translations, you make any time independent Lie definition for coordinates x. Time translations will work with any coordinates. So we'll do this discussion more abstract. Okay, so under a time translation, what does qr? Suppose we got some coordinates qi. We make a small change in q. Qi prime then is equal to qi plus what to first order?
Q dot.
What? Q dot. Excellent. Qi dot. Why? You see, what we're doing is to say q prime of t is equal to q of t plus epsilon. That's what the time translation is. And then we take and expand that function in the power series next expression. So that is q plus q dot times epsilon plus order epsilon squared, which we know. Okay? So the coordinate change, the change of our functions that comes from a time translation is this. Now we're going to apply our formula to this process. But before we do that, we have to ask, does the Lagrangian remain invariant under time translations? Or is that true? Or is it only the action? Okay? So the derivation of Noether's theorem was keeping track of first order changes. We looked at continuous symmetries and worked to first order and the expansion around identity.
But time translation should be valid for any amount of time, right?
That is true. All of the symmetries we looked at have finite versions. So translation invariance in space also is true when you're translating arbitrary ones. But in order to derive what we need, we only are going to use the fact that it's true infinite.
We can apply it.
We can have successive. That's right. So while it is true, more generally, we are only using the fact that it's true infinite. Okay? So that you can't stop me from doing. Anything I prove from here will be true. I mean, this is a special case of what you do. Now, as you pointed out, actually you don't lose much information by going to the special case because you can argue. Okay? Good. So, now let's see how the Lagrangian changes as a function of time. It's obvious, but I'll do the algebraically just so that's not confusing. Okay. So, this is the change in coordinates. So, what is the change in the Lagrangian? It is epsilon here is taken to be constant. We're just asking how the Lagrangian changes under the symmetry transformations. Because that's how you define the H. For the definition of H, you did not need epsilon to be a function of time. So the change in the Lagrangian is equal to del L by del Qi, delta Qi, which is epsilon Qi dot. Okay? Plus del L by del Qi dot epsilon Qi dot. So that's the change in the derivative. But this, of course, and this thing that was solving is just d by dt. It's not calculated of A. I mean, I got this expression by expanding it. under time is simply the time derivative of the Lagrangian. This was an obvious statement. It was as obvious as the statement that the change in Q was the derivative of Q. It's true of every function. The change of any function in the world under a small time translation is the derivative of that function. Of course, right? Yeah. So, we've identified H. H is equal to N, the Lagrangian. Is this clear? Now, we're almost home. So we're almost home. Where are we? So our conserved charge was d by d. What was it? It was del by del qi dot times delta qi, which was qi dot, minus n. This is the conserved charge. It's called the energy.
In general, it is a Hamiltonian. But for conservative system, it reduces to Fourier.
Right. It's true that this object is subject called the Hamiltonian. It's called the Hamiltonian when you express it as a function of momentum. Yes. But that is not of importance to us. At the moment, yet. It will be. But at the moment, this is a conserved quantity. It is independent of time for any solution to the equation of motion. This is a quantity we call the energy. Okay? Let's evaluate this quantity for our special Lagrangian using the coordinates xi dot. Actually, we could use it. Let's do it first. Special Lagrangian using the coordinates xi dot. Okay, xi. Now, what is del? Look. Our action, our special action, could be written as a sum of kinetic energy minus sum of potential energy. Just names. Okay? Where T was equal to sum over I, mi, xi dot squared by 2, and V was equal to V. Now, when we replace qi by qi dot, what do we get by del L by, so L is equal to T minus V. What is del V by del qi dot? 0. Because V is a function only of x. Okay? So this quantity gets contribution only from T. Now, del L by del qi dot times qi dot. Yes. It's easy to evaluate, but on structural grounds, this is equal to 2 times T. This is Euler's theorem. You see, T was a homogeneous functions of the xi dots of degree 2. So if you've got any homogeneous function of some variables, and you do A d by dA, summed over all its variables, you get homogeneity times the original function. This is an obvious statement. But Euler was the first to make it, so he got his theorem. That was name of that. Okay. So, this object is 2t, and the Lagrangian was t minus v. So we get minus t minus v is equal to t plus v. So the energy function in the special case we're talking about is the sum of T and V, and this justifies the names kinetic energy for T because it's the energy of motion varying with velocities, and potential energy for V because it's the energy independent of motions. Blah, 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 you know. Okay. So the energy function is kinetic energy plus potential energy in this special case. Once again, all of this you knew, right? You know from the 12th standard, it's not sense that for earlier, you know that energy is conserved and you know what energy is for such systems and momentum systems, angular momentum systems. You might think, what have I learned from this? And for this system, in some sense, in a practical way, you've not learned much. But the point here is this, at least for those of you who are interested in theoretical work, it's very rare that we actually, in research today, do research in classical mechanics. Engineers do, or not research, they work with it all the time, but theoretical physicists, most of you will not. The point of this course, more than to learn how classical mechanics works, is to learn about the techniques of quantum physics. In a context where intuition helps you understand abstract concepts. Okay? So what we are seeing here is how very familiar things you know very well, conservation of momentum, conservation of angular momentum, conservation of energy, come out as direct consequences of symmetries of the system in a manner that is easily generalizable to much less familiar situations. That is the point of this exercise. Okay. Now, there is an exercise that, okay, see, you guys, we have problem sets more or less every week. I'll give you the first one next class. But one of the problems on the problem set will be, what is the conserved charge that follows from boost invariance in the system? You know, we've argued that every symmetry leads to a conserved charge. Boosts are a symmetry, Lagrangian transformations are a symmetry, they should lead to some conserved charge applying our procedure. But now you might feel, now I'm onto something new, because I've heard all the things I've heard of are exhaustive. So this new conserved charge, this must be something that Resnick and Halliday missed. Okay, that's not true. You don't miss something in teaching a 200-300-year-old subject. Okay, there's no new conserved charge. It turns out that the quantity that is conserved by this procedure is go on. I can't. Just say again.
Epsilon dt h2y as the change in the Lagrangian as epsilon dt h2y plus epsilon dot g.
Yes. Yes.
I bring the dt out. This is a total derivative of a function. The Lagrangian, the linear infinity says the Lagrangian will be variant because if you bring respect to the differential.
Right.
And then the entire procedure has been somewhere written in that Lagrangian because the dt is out, the h t of I is something like dt of.
Okay, why are we working out? Explain. You see, the procedure does apply to the linear transformation. It applies to any coordinate transformation. The point is that the quantity that you get is not new. The quantity that you get that is conserved is automatically conserved once momentum is conserved. But I want you to work with substitution. Because this will be one of your exercises. Apply this procedure to the linear transformations. See what you get and show that there is no new information from it.
Actually, that's obvious, right? Because if you have constant velocity, you take it for a finite period of time, so vt, that's equivalent to a translational variance, right?
But you know, translation doesn't change velocities. Boosts do. Maybe it's obvious to you, that's great. It's not totally obvious to me. I mean, without doing it.
Yeah, how can it change the velocity? You are assuming constant velocity, right? The Galilean boost is xi dash is equal to xi plus vt, right?
Okay, now you can say that. Xi dash dot is equal to xi dot plus v. So it changes velocities.
So if it doesn't give any new conserved quantities, can it mean that somehow it arises from the homogeneity in time or the homogeneity in space?
From what?
Because it doesn't, Galilean boost don't give a new conserved quantity, can it mean that it is a natural consequence of homogeneity in space and time.
No, but it's possible to make theories that are homogeneous in space, rotational event, time translation event, but not relativity. For instance,
But which follow that we have a Lagrangian dynamics.
yeah, in some sense, I mean, maybe in some sense that's true if you have it. No, but once again, suppose we took our Lagrangian and made it mi(xi) dot to the 4. Okay? Plus rotational invariant potential. This thing will now continue to be invariant under spatial translations, spatial rotations, so it will not be under invariant under derivative. Okay? So it's not, I don't think the following statement is true, that every system that is rotationally and translationally invariant and time translationally invariant is also necessarily derivative. That is not true. In fact, special relativity theories and special relativity have the first three symmetries, but not the fourth. It's one of it. Okay? So, yeah. Now, you can ask, what does it mean that it doesn't give you an additional conserved charge? There's probably something to say.
In relativity, the form of the Lagrangian changes. You don't have it directly proportional to V square.
That's true, but what is not changed is that it's translation invariant, rotational invariant. So it's not true that every Lagrangian that has the first few symmetries also is necessary.
And then this pertains to what you said tomorrow, that when you have an LV square, you come up with an LV square, and then you take this. I didn't understand how can you make it proportional to V square?
By giving form Lagrangian invariance.
Forget it. So if instead of Lagrangian invariance, we have Lorentz invariance,
Then it changes. Excellent. Okay, so this will be one of the exercises in your problem set. Let's move on. We'll discuss it more once we're done. Your problem set. Okay, now you guys don't have anything particular now, right? I'm going to take 5-10 minutes. That's okay. There's a lot we want to say in this course. We want to at least go through this book by Lagrangian, and then if there's time, we'll do more fun. Okay, but at least we want to go through this. So let's keep moving. Okay, so I'll take maybe 5-10 minutes extra each class, provided this information. Okay, so fine. So now we've gone through these conserved charges. There are 2 or 3 things that I want to that you should describe in this chapter that I want to do. This is we're now discussing chapter 2 in here. Okay? There's this about center of mass that I'm almost sure if you're familiar. But let me just very quickly say it, and then I'll talk about the more interesting things about like the video theories. Maybe center of mass. I'll say it next time. I'll tell you what the center of mass is. All of you know it, it's very familiar. I'll tell you about that next time. Then tell you about the remaining interesting things. I mean, the couple of things that are really interesting. In class. Okay. So there are 2 things I want to tell you about coin in these class. And the first thing is something really nice. It goes this way. Suppose we got a Lagrangian of the form we keep talking. mxi dot squared by 2 minus b or xi. Okay? And suppose it's true that v of lambda times x is equal to lambda bar a. That is, the potential function is a homogeneous function of the coordinates with homogeneity A. Okay. Now, so far we talked about of dynamics. And now when we talk about two specific dynamical things, you can say about Lagrangians of this form, but on rather general structural grounds, without doing any calculations. Okay. The first thing I'm going to explain to you is that any such Lagrangian has an effective scale transformation symmetry in a sense I will tell you about now. Okay, so suppose this is true. Then let me look at the variable change x twiddle ni is equal to lambda to the power alpha, and I'll fix what alpha is in a moment, of t of x ni of lambda times t. Okay? So, suppose I evaluate the Lagrangian as this Lagrangian as a function of x. Maybe I should put the exponents here. I evaluate this Lagrangian as a function of x and I t, and then substitute in this expression for x twiddle. Okay? The question I'm going to ask is what do I get? Okay, so let me do this. I take this Lagrangian and just substitute it into it. Now, every time I have a derivative, I put up an additional factor of lambda from here. Okay? And every time I have an x, I put out an additional factor of lambda to the alpha, and from here I put out an additional factor of lambda to the power alpha times a. Okay, so this quantity becomes dt, okay, times x twiddle n d by dt of I the whole thing squared, lambda squared from the here, that's lambda to the power plus 2 alpha. Whereas this quantity here becomes minus lambda to the power 2 to the power alpha a v. Yes. Yes. So I take this expression here and I plug it in. Okay? And I just evaluate everything in terms of x twiddles. Just take this object and evaluate it. Okay? Now, in general, of course the Lagrangian changes in a complicated way. But in the special case that this and this factor are the same, the Lagrangian just changes by an overall constant. Okay? And if you have two different Lagrangians that are different by an overall constant, you get the same equations of motion. Okay? So what we have just deduced, and I'll say this again, I shouldn't hurry through this. I'll say this again and probably next class. Let me just give you the punch. What we've just deduced is that if x of t is a function, is a solution of the equation of motion for such a Lagrangian, then so is lambda to the power. So we have to find alpha such that these two are equal, but that is alpha is equal to 2 divided by a minus 2. Oh, I should have put the there's not. I should have done it differently because you put lambda here. Sorry. This singular a equals 2, which is the harmonic oscillator which I wanted to tell you. Among other things. Let me do this. Okay, so now I get 2 plus 2 beta plus, and this is just lambda to the power a. Okay, so this solution is simpler. We want to equate these two, so we get beta is equal to a minus 2 divided by 2. Okay. Better. Okay. Now, I'll tell you about this in more detail in this class. We should stop in a minute or two. But just to say, so that if we've got a solution, x will, we have another solution by scaling x and scaling time in this coordinated fashion, where beta is equal to this. Okay? What does this mean? This means that, okay, so now let's take particular examples. Firstly, let's take the example a equals 0. There's no potential. The potential is a constant, same thing there, no potential. That tells you that you've got a symmetric, you've got, given a solution, you get another solution by expanding time and space by the same amount. Okay? Which physically is that if you've got a particle moving at constant velocity and moves distance x and times t, it'll move distance 2x and times 2t. Okay. Let's take a equals 2. Okay, let's take a equals 1. This is the case of a linear potential. Okay? In this case, this quantity becomes minus half. Okay? This quantity becomes minus half compared to 1. That is the statement that that x is equal to t squared under a fall of gravity, constant acceleration. Okay, the distance that we move is proportional to the time squared. We'll see all this in more detail next class. Just waiting here at that. Okay, what about a equals 2? This is the case of harmonic oscillator. This tells you that no matter how that you scale x, you don't scale time. It's the statement that the frequency of a harmonic oscillator is independent of its amplitude. Okay? And now let's take the case, another case, a equals minus 1. This is the case of the Newtonian potential. This tells you that the scaling is, if you scale x by x goes to lambda x, this t goes to with the power 3 by 2. This is Kepler's law. It tells you that the time period of rotations scales like the 2/3 power of the radius. Okay, we understand this. There's a minus sign here that I have to explain to you properly. We'll understand this in more detail next class when we have a little more time. Okay, but just to make you appetite about this, and the last making of appetites, but it's very important. Okay, the last thing I want to prove about this thing. So the next class, what we'll do is we'll go through this more carefully. We'll talk about central points, and then I'll start to learn problems to make this more concrete. Okay, the last thing I wanted to talk about was the following. Okay, suppose you have actually we're even out of the tape. Let me stop about this. Stop here. It's okay.